So as promised, here's an instructional video on section 6.5. We're going to talk about numbers in the complex plane. So remember that a complex number looks like this, a plus bi, where a is the real number part, and I, which is defined to be the square root of a -1, we often call imaginary. So a number a plus bi. Okay, how are we going to graph this? Well, instead of calling this the x-axis, it's the real axis. So this is what you would count for the a part, and this is the imaginary axis. So the number 3 plus I would be over 3 and then up 1 because the b would be a 1 there. The number -2 comma -I would be to the left 2 and then down 1 because b is a -1. Okay, the absolute value or modulus of the complex number is the distance between the origin and the point. So if we were going to find this distance here, it's very much like finding the magnitude of the vector in the previous section. The absolute value of a complex number is the square root of a squared plus b squared. Please walk through the example. It's pretty straightforward math. We can do some operations with numbers in the complex plane. You can go ahead and read this, but the only thing that you need to know is how to add two complex numbers, and I believe you did this in Algebra 2. You'd add the real number part. 1 plus 2 would give you 3, and then you'd add the imaginary parts. 3 plus 1 would be 4i. It's kind of interesting to look at how they can draw a diagram of that in the plane. So you can add and you can subtract numbers in the complex plane. Let's take a look at what a complex conjugate looks like graphed. So z stands for any complex number. And remember that a conjugate just means to change the sign that's in the middle. So for instance, if we had 3 plus I, the conjugate would be 3 minus I. In the book on example 4, we have -3 plus I. The conjugate would be -3. That doesn't change, but this sign changes. Those are called conjugates. And when you graph those, looking at this graph, the number and its conjugate, they are reflections over the real axis. So that's kind of an interesting thing. We can find, okay, the distance between two complex numbers. I would have you go through this. This again is very much like the length of a vector that's not in standard position starting at 0, 0. So it's very much like x2 minus x1 quantity squared plus y2 minus y1 quantity squared, the distance formula, right? And just to note here, if you have two complex numbers, let's take a look at this. Find the distance between 2 plus 3i, so that's some number, and 5 minus 2i. And here they have that graphed. 2 plus 3i would be here, and 5 minus 2i would be here. What is this distance? Well, you just subtract your x's. So they did 5 minus 2 quantity squared, and then subtract the y's, -2 minus 3 quantity squared. And what I wanted to make a point of here, you could change the order of these because when you square it, you would get a +9. So 5 minus 2 is 3, squared gives you 9. If you reverse that, you'd have 2 minus 5, which is a -3. Quantity squared would still be a +9. So the order doesn't matter here. What matters, those are both the A's and these are both the B's. A, B, A, B. Okay. Next up is the midpoint formula. Just like we find the midpoint of any line segment, we add the x coordinates and divide by 2, comma, the average of the y coordinates. So these are the A's, the real number parts, and these are the imaginary parts. So here's an example. Let's find the midpoint of 4 minus 3i and 2 plus 2i. So we take the 4 and the 2, add those together, divide by 2. 6 divided by 2 is 3. And then you take the b's, negative 3 and positive 2, which is a negative 1 over 2. So this point 3 minus 2i, 3 minus 2i, that's a complex number that is at the midpoint of between these 2 points in the complex plane. So it's really all the math you have done before. It's just kind of looking at it differently, looking at it as complex numbers. And that's about it. If you have any questions, please reach out, or we can go over these on Monday morning. See you then.